Good day, everyone. My name is JC, and I'm the group leader of the group 2. Today, our group will be presenting our group project titled Designing an Effective Campus Network Using the Discrete Mathematics. This project focuses on how mathematical concepts can be applied to design a network that is both effective and cost-effective. First of all, this is our team. Next, let's look at the background of the problem. Internet connectivity is essential for an university operation, especially in the campus with multiple buildings. Each building requires a stable and continuous access to the network. Therefore, a network must be fully connected, efficient, and cost-effective. This means we need to ensure all buildings are connected while minimizing unnecessary connection and overall costs. After that, we model the campus network using discrete mathematics. In this model, buildings are represented as vertices, and the connection between them are represented as edge, which may include the weights such as cost and distance. This allows us to represent the entire network as the graph model, making it easier to analyze. On the right, we can see a simple example of the graph. Each node, such as A, B, and C, represent a building, while the line connecting them represent the edge or connection between the buildings. For example, A is connected to the B and C, and B is connected to C, forming a small network. This visual representation helps us clearly understand how different buildings are connected. This purpose of our project is to apply discrete mathematical concept and analyze the structure of the networks and determine the most optimal and efficient solution. To achieve this, we use three main approaches. First, mathematical induction, which helps us prove the relationship between the number of vertices and edge. Second, graph modeling, which allows us to visually represent the campus network. Finally, tree and minimum spanning tree, which help us optimize the network by reducing costs while maintaining full connectivities. Now, let's move on to part A, mathematical reasoning and proof using induction. In this part, we will focus on the relationship between the vertices and edge. First, we identify the pattern of how the network grows, and then we use mathematical induction to prove that this pattern holds for all the case. The diagram shown here is a simple example of the network, where buildings are represented as vertices and connections are represented as edge. This helps us visualize how the network expands step by step. To begin, we visualize how the network grows. The network develops step by step, where each new building adds one additional connection. Therefore, a pattern is formed: 0, 1, 2, 3, and so on. For example, when n equals to 1, there is one vertex and 0 edge. When n equals to 2, there are two vertices and one edge. We continue observing the pattern. When n equals to 3, there are 3 vertices and 2 edges. When n equals to 4, there are 4 vertices and 3 edges. This shows a clear relationship between the number of vertices and edge, where the number of edge is always 1 less than the number of vertices. This forms a tree structure. Now, we translate this into a mathematical representation. Buildings are represented as vertices and connections are represented as edge. The network must satisfy the following condition. It must be connected and it must be cycle-free, meaning no redundant connection. Therefore, our objective is to minimize the number of edges while still maintaining full connectivity of the network. Next, we can state the general relationship. Let n represent the number of vertices or buildings in the network. For a connected and cycle-free network, the number of edges is always n minus 1. The diagram on the right is a simple example of a tree structure included to illustrate this relationship visually. This showed that in a graph theory, a tree is a connected structure without cycle, where the number of edges is always one less than the number of the vertices. To prove this, we will use mathematical induction. First, we consider the base case where n equals to 1. In this case, there is one vertex and 0 edge. Using the formula n minus 1, we get 1 minus 1, which is equal to 0. This matches the actual number of the connection. Therefore, the statement is true and for n equals to 1. Next, we proceed to the inductive state. We assume the statement is true for n equals to k, where the number of edge is k minus 1. Now we consider n equals k plus 1. When we add one new building, it requires exactly one additional connection. So the total number of edge become k minus 1 plus 1, which equals to k. This matches the formula since k plus 1 minus 1 is also equals to k. Therefore, the statement is true for n equals to k plus 1. So, from the base case and the inductive step, we can conclude that the statement is true for all value of n greater than or equals to 1. Therefore, the formula of n minus 1 is valid for any connected cycle-free network. Finally, we justify the use of mathematical induction. The network grows step by step, and each new building follows a consistent pattern. The number of edges form a sequence, like 0, 1, 2, 3, and so on. Therefore, mathematical induction is an appropriate method as it proves that this relationship holds all value of n. Alright, that's all from me for my part A on the mathematical reasoning and induction. Thank you for your time, and now I will pass the presentation to my group member to continue with the other section.
Assalamualaikum warahmatullahi wabarakatuh to Madam Khairun and a very good day to everyone. My name is Siti Nur Shafira binti Manazmi. Today I will continue the explanation of the graph modeling of campus network. In this project, we model the campus internet network using a graph. Each building is represented as a vertex, while the cables connecting them are represented as edges. This approach allows us to simplify complex network relationships into a clear mathematical structure. Next, I will continue to explain the weighted graph representation. Each cable connection is assigned a weight, representing either cost or distance. For example, the link between A to B is equal to 4, A to C is equal to 2, B to C is equal to 1, B to D is equal to 5, C to D is equal to 8, C to E is equal to 10, and D to E is equal to 2. This makes the graph a weighted, undirected, and connected graph, meaning all buildings are linked and accessible. Next, in a real-life application, this graph model helps engineers to visualize the network structure. It allows them to plan cable layouts efficiently, compare costs, and identify the most practical way to connect all buildings. Next, to optimize the network, we apply the concept of a minimum spanning tree. This ensures only the most essential connections are kept, avoiding unnecessary or costly links. As a result, the campus achieves full connectivity at the lowest possible cost. Next, I will pass to the next presenter.
Thank you, Fira. My name is Zara Fatiha and I will explain about the Hamilton parts. Okay, so now I will continue from the graph that was introduced earlier. As mentioned, each building is represented as a vertex and each connection is represented by an edge. Based on the graph, we will now explore another concept in the graph theory, which is the Hamilton path. A Hamilton path is defined as a path that visits every vertex exactly once, without repeating any vertex. This means we must pass through all the buildings, but we cannot visit the same building more than once. Now, referring to the diagram, we can identify one possible Hamilton path, which is, for example, we can start from vertex A, then move to the vertex B, and from then we go to vertex C, and followed by D, and the last one, it will be E. This path is considered valid because first it visits all the vertex in the graph, and second, each vertex is visited only once, and third, all movements from following edges in the graph. Therefore, it satisfies the definition of a Hamilton path. However, it is important to note that a Hamilton path does not focus on cost optimization. Unlike the minimum spanning tree that we discussed earlier, which aims to minimize the total cost of connection, a Hamilton path only focuses on finding a value root that visits all vertices once. In conclusion, the Hamilton path helps us understand how a network can be traversed completely, while the minimum spanning tree helps us design the most efficient network. Both concepts are important, but they serve different purposes in graph theory. Thank you. I will pass to the next presenter.
Assalamualaikum and good day everyone. My name is Nur Syafiqah Nasha and now I will present part C, which is tree structures and algorithm efficiency. To begin with, I will explain the concepts of tree and spanning tree since these are the main ideas behind optimizing the campus network. In this campus internet network, each building is represented as a vertex and each connection or cable is represented as an edge with a weight showing cost or distance. So, the graph is a representation of the network. A tree is a connected graph with no cycle. In the campus network, this means all buildings remain connected, but there are no loops. This is important because loops do not improve connectivity when all buildings are already reachable. Instead, they only increase the cost of the network. A spanning tree is a subgraph that connects all buildings without forming any cycle. Okay. In general, for n buildings, the number of each is in a tree is n-1. Based on this concept, we use the minimum spanning tree, or we call MST, because it connects all buildings while using the least possible cost. Next, I will present how Kruskal's algorithm is used to find the minimum spanning tree step by step. Okay, to find the minimum spanning tree, or we call it MST, we use Kruskal's algorithm. This algorithm works in three main steps. The first one, sort all edges in ascending order of weight. Second, select the smallest edge. And third, avoid forming cycles. So, the first one, the edges are arranged from the smallest to the largest weight, which are BC with 1, AC with 2, DE with 2, AB with 4, BD with 5, CD with 8, and CE with 10. Next, we select the edges step by step. we choose BC because it has the smallest weight. Then we choose AC, followed by DE, since both do not form any cycle. After that, AB is rejected because it would create a cycle among A, B, and C. Finally, we choose BD because it connects the two separate components without forming a cycle. Therefore, the final MST is BC, AC, BD, and DE with a total cost of 10. This diagram shows the minimum spanning tree of the campus network. We can see that all buildings are connected using only the necessary connections, which are AC, BC, BD, and DE. The structure is a tree because it is connected and has no cycle. This means every building can still be reached, but there are no unnecessary loops. So, this diagram clearly shows the optimized form of the campus network. Lastly, I will explain why this solution is efficient and how it minimizes cost in the real campus network. Okay, the MST is efficient because it reduces the original graph from 7 possible connections to only 4 connections, while still keeping all buildings connected. This means the network becomes simpler and more cost-effective. Kruskal's algorithm helps achieve this by always selecting the lowest weight edges and avoiding cycles. For example, AB with weight 4 is rejected because A, B, and C are already connected through AC and BC. So, adding AB would only create a cycle and increase the cost without improving connectivity. This shows that no cycle means unnecessary connections are removed. At the same time, minimum cost means the network is more efficient. In real campus network, this is important because using fiber cables reduces installation costs, makes maintenance easier, and improves the use of available resources. Therefore, the MST is the best optimized solution for the campus network. In conclusion, the campus internet network can be effectively optimized by transforming the original graph into a minimum spanning tree or MST. By applying Kruskal's algorithm, the most suitable connections selected are BC, AC, BD, and DE with a minimum total cost of 10. This means that all buildings are successfully connected while avoiding any cycles. This solution is valid because it follows the fundamental property of a tree where a connected graph with n vertices contains exactly n-1 edges. Since our network has 5 buildings, the MST contains 4 edges, which ensures full connectivity and efficiency at the same time. The result also shows that removing redundant connections is important. When cycles are avoided, unnecessary costs can also be avoided, so the network becomes simpler but still fully functional. In addition, the step-by-step process of Kruskal's algorithm shows how the algorithm systematically chooses the lowest weight edges while preventing cycles. This proves that algorithmic methods are very useful in solving real-world network design problems. In a practical campus setting, reducing the total cost of connections can lower installation expenses, make maintenance easier, and improve the use of available resources. Therefore, the MST not only ensures full connectivity, but also provides a cost-efficient, reliable, and optimized solution for designing an effective campus internet network. Okay, that's all from me. Thank you.